Okay, I want to tell you about something that's been hovering in the background of our discussions lately, and that's about the standard basis vectors. I just want to make it explicit. So in R2, for example, in the plane, right, we have these special vectors, which are called usually I and J, or I hat maybe and J hat, and that's the vector 1, 0, sort of the unit vector in the x direction, and J hat 0, 1. Okay, so right, if we drew our standard axes, then I hat is like right here, right? And J hat is right there. Okay, and this is a nice, I mean, these are kind of the standard vectors that we talk about, that we base everything off of, because it's easy to write every vector in terms of I and J. And in fact, it's nice because every single x, every vector x, right, there's a vector x1 comma x2, can be written in terms of I and J, but moreover, can be written uniquely, i.e., by that I mean with in one and only one way. As a linear combination of I hat and J hat. So every vector can be written, yeah. In terms of I hat and J hat, this is obvious. It's just worth saying. A lot of things we say in math, we say obvious things to make them just very explicit. So, so by that I mean, right, if you write x, we can break that down as x1 times 1, 0 plus x2 times 0, 1. And that's x1i hat plus x2j hat. And that's the only way to write any vector in terms of I hat and j hat, right? And so that's actually going to be a very important idea, that the idea of every vector in our space being a unique linear combination, not just like a linear combination, but like a unique linear combination. And so just because of this, I hat and j hat are called the standard basis. We're going to use this word basis actually pretty soon, but basis just means like, I mean, it has a technical definition, but it also just means sort of the base that you build up everything, right? We can build up every vector in the plane from I hat and j hat. Okay, so all right, so so really I just want to generalize this to more dimensions, right? So similarly, we have I hat, j hat, and k hat, ijk if you prefer. In R3, right, so the unit vectors in the x, y, and z directions. But let's think about what would happen in R4. So we could write the vectors the four vectors would look like this, right? 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And should we call them I hat, j hat, k hat, l hat? No, you know, it's this kind of same thing. When we systematize, we're going to run out of letters. So people tend to call these E1, E2, E3, E4. So we're going to use subscripts instead. And, you know, that's going to, well, we'll talk about that, just generalizes to n dimensions immediately. We have E1 through En. We could have even called I hat and J hat in 2 dimensions, just E1 and E2, which you'll see in textbooks and stuff. But just before I say the general n-dimensional thing, I just want to note something. If we look at the matrix made up of these vectors. So if I actually write the matrix whose columns are E1, E2, E3, and E4, that's this really nice looking matrix, right? It's 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It's this matrix where there's a 1 on the diagonal, zeros everywhere else. It has a special name. Well, I just want to mention it. This is a vector that's already in reduced echelon form. Already reduced. And it has, it's sort of the nicest reduced echelon form for a square 4x4 matrix, right? It's sort of the nicest, meaning no free variables, right? Nothing weird. It's just basically if you had a pivot, you know, as you went down in every column and every row. It's just 4x4 reduced echelon form. And so it has a name. It's called, this matrix is called the identity matrix. You may have already come across. The identity matrix. And it's written as I. It's called I, or maybe I sub 4 if you want to note that it's a 4x4 matrix. Okay. And the reason this is also another reason this is so nice is it tells you something about these 4 vectors, right? The fact that there's a pivot in every row means that these vectors span all of R4. I mean, it's kind of obvious, right? We can write every vector in terms of these. Ooh. That's all of R4, so it spans the whole space. And the pivot in every column means that the vectors are linearly independent, which is also pretty obvious that there's no way any of them could be a linear combination of the others. So pivot in every column implies linear independence, right? Okay. Yeah, so just similarly, if we kind of in general, just as the last thing to say, in general, we have these standard, we have in n dimensions, we would have these n vectors, E1 through En, where EI is the vector, you know, with zeros, and then there's a 1. There's a 1 in the ith position, right? So that is in the ith position. And this is called the standard basis of Rn. And the matrix, the matrix of them is called the n by n identity matrix. Or just, again, you could just use I and not In if the context is clear. Okay, so it's going to be useful to have all this terminology, but I will stop there.